When we were together in class, we talked about what the first derivative had to tell us about the graph of a function. So here I am on a Desmos file linked in the resources for the week, and I've got a function with a draggable point. And off to the right, I have Desmos calculating the first derivative of the function at that point. And again, that first derivative is telling us about the slope of the tangent line. So you can also turn on the tangent line just to see. So any place where the function is decreasing, you're going to see the derivative, the first derivative, be a negative number. So as I'm pulling this line along, first derivative is a negative number. But then when I get to the spot where the function is increasing, the tangent lines go positive, and of course the derivative is positive. And then once we start decreasing, the tangent lines are going to be negative. This one's briefly going to stop off at 0 here at 1, and then head down towards negative again for decreasing. All right. But now we want to talk about what is the second derivative telling us about the function. So I'm going to turn off this tangent line, and I'm going to turn on the second derivative. So let's head back over to the left. And the second derivative at this point is actually quite large. It's a positive number. And unlike the first derivative, it doesn't change sign whenever we switch from increasing to decreasing. We're still positive. We were positive back when we were decreasing too. For the second derivative, I've got positive numbers. What the second derivative is going to tell us about is the concavity of a function. And when we say concavity, we kind of mean whether it looks a little bit like an upward opening parabola or a downward opening parabola. So we're going to say that a function is either concave up like a cup or concave down like a frown. So over on the left-hand part of this graph, where the function is concave up, you can see that the second derivative is positive. And then right about in here somewhere, we see it change from positive to negative. So this portion of the graph is where the function is concave down, and it has negative second derivative values. And then ever so slightly, it's going to change to positive right about there, okay? Because there's this little segment of the graph that sort of looks like a teeny bit of an upward opening parabola. It's concave up for a while, and then after it passes this x-intercept, we are concave down again. It looks like part of a downward opening parabola, concave down like a frown, negative second derivative. The last folder that I've got in this Desmos file is labeled Inflection Points. Those 3 points are the spots where this function changes from concave up to concave down, or concave down to concave up. So those spots are called inflection points. They're a little bit harder to spot just looking at the graph than the changes in the first derivative were. Just briefly, I want to talk about why the second derivative tells us about concavity. I've got a function here that's half concave down and half concave up. So I'm going to look at a place where this is concave up. So that would be the right half of the graph. So from 0 and onward, this function is concave up. And I want us to think about the tangent line. So I'm going to try to draw 2 tangent lines to this function, one that's down here pretty close to the origin, and I'm just approximating here. And then I'll draw another one over here. And you can kind of imagine if we were on Desmos being able to let those tangent lines slide up the graph. So the tangent lines in this pink section of the graph, those green tangent lines, are increasing in slope. So in this concave up section, so concave up, remember concave up like a cup on the right half of the graph here. In the concave up section, the slopes of the tangent lines are increasing. And we know that the slopes of the tangent line are given by the derivative. So this means that f prime of x is increasing. And f prime of x increasing, remember what it means for a function to be increasing. That means its derivative is positive. So if f prime is increasing, f double prime has to be positive. Likewise, we can kind of make the same argument when the function is concave down. So that's going to be the left half of the graph. If I look over at the left half of the graph where things are concave down, if I draw myself a couple of tangent lines there, and again, just kind of an approximation so we can see, over here on the left portion, the tangent lines are going to be very steep and have large slope. But then as they go along the graph, they're going to have to flatten out. Okay, so the slopes of these tangent lines as they slide along the graph are decreasing in value. So when we're concave down, our slopes are decreasing. They went from steep and getting flatter. So our slopes are decreasing. Again, if slopes are decreasing, f prime is decreasing. If f prime is decreasing, that means its derivative is negative. When a function is decreasing, its derivative is negative. So its derivative, f double prime, is negative. So here we're associating a second derivative being negative with concave down, second derivative being positive with the original function being concave up. All right, so this is just a summary. On any interval where the second derivative is positive, the original function is concave up. Where the second derivative is negative, the original function is concave down. So now we're going to find the intervals where this function is concave up or concave down. This is going to look just like finding intervals of increasing and decreasing. We're just going to do that sign chart with the second derivative rather than the first derivative. So we're going to find the second derivative of this function. We have to pass through the first derivative. So let's find f prime of x. So my negative will go along for the ride. Derivative of x cubed is 3x squared. Let's see, 3 halves times derivative of x squared, which is 2x, and then plus 18. All right, so simplifying a little bit, these 2's will cancel. And I get negative 3x squared plus 3x plus 18. Then we can find our second derivative. So f double prime is going to be the derivative of that quadratic. So we're going to get negative 6x plus 3. So just like when we were finding increasing, decreasing chart, we want to figure out where this derivative is equal to 0. So let's set second derivative equal to 0. Subtract 3 from both sides. So I get negative 6x equals negative 3. Divide by 6, negative 6. And I get x equals, that's going to be a positive 1/2. So now, just like we did with the increasing and decreasing chart, we're going to make a sign chart, this time with the second derivative. So I'm going to make my number line. I'm going to put that 1/2 that I solved for, where the second derivative was equal to 0. So we're going to make statements about f double prime on top, and we're going to make statements about the actual function on the bottom. So again, we pick any number that we want to in each region. So I'm going to pick something that is to the left of 1/2. 0 is by far the easiest choice. So I'm going to find f double prime of 0. And something to the right, I'll find f double prime of 1. Again, you don't have to pick 1. Pick anything to the right of 1/2. You can pick 100 or 100 billion, whatever you want. You're going to get the same answer no matter what. All right, so I'm going to find f double prime, that's this function here. Let's find f double prime of 0. So that's negative 6 times 0 plus 3. That gives me something positive. Again, I only care that this number is positive. And do the same thing, f double prime of 1. F double prime of 1, negative 6 times 1 plus 3. Negative 6 plus 3 is negative 3. Again, I'm most concerned that that is something negative. All right, so let's make our statements about the original function f of x. So we know when the second derivative is positive, our original function is going to be concave up like a cup. So in this region, we're going to be concave up. In the second region, we're going to say that the function is concave down. So concave down like a frown. All right, so let's make our statement. We're going to say that f of x is concave up on negative infinity to negative, to 1/2. And f of x is concave down on 1/2 to infinity. And again, we're always going to write those as open intervals with parentheses. Precisely at x equals 1/2, this function is neither concave up nor concave down. It's kind of in the process of switching between the two. So since we changed concavity at that point, x equals 1/2, we're going to say that we have an inflection point at x equals 1/2. So we're going to say we have an inflection point at x equals 1/2.